In today's video, we're going to talk about solving the reaction forces of a simply supported beam. To do that, we're going to continue using what we've been practicing with our equations of equilibrium and our properties of sine and cosine to break our forces down, our vector forces down into x and y components. So, just jump right in. I've got a simply supported beam here with pinned support at A, roller support at B. On top of that beam, I've got a force F1 acting 50 degrees down into the left, or sorry, 50 pounds down into the left, and that's at 60 degrees from our horizontal beam here. And F2 is acting 50 pounds straight down at point B. Points A and B are 10 feet apart, and force 1 is acting 4 feet from point A. So from there, let's break that down into a free body diagram, which I've drawn off to the side here a little bit. And at point A, I've replaced my pinned connection with two reaction forces, force A in the x direction and force A in the y direction. And then at point B, since it's a roller connection, I've replaced that with one reaction force perpendicular to my beam, and that I call FBY. My other two forces come with, along for the ride. And maybe before we begin, let's break down force F1 into its x and y components. So since it is going down and to the left, I know that I have a portion of this force acting to the left, and I have a portion of this force acting straight down. So we'll call that F1x and F1y. So let's solve for that before we start doing our equilibrium equations, so there's less to work and write down later. So F1 in the x direction is going to be equal to F1 times the cosine of our theta angle. Remember, anytime we have our angle in relation to the x-axis, our x component of the force is the force times the cosine of the theta. F1y will be F1 times the sine of theta. So similarly, anytime the angle is at the x direction or in relation to the x-axis, it's the force times the sine of whatever the angle is. So let's write that out. 50 cosine of 60, 50 sine 60. Okay, so make sure as you do this, if you don't remember your properties, like I always end up forgetting, use your calculator and make sure your calculator is in radians. Or not in radians, excuse me. Make sure your calculator is in degrees, excuse me. Let me reiterate that because I said it wrong. It must be in degrees, not radians. So I did sine first, so that one is 43.3 pounds. 50 cosine 60 is 25 pounds. Okay, so there's F1x, F1y. So let's break down now our equations of equilibrium so that we can solve ultimately for all of our reaction forces here. So I will work across. So the sum of my forces in the x direction are always equal to 0, and all of my x forces are FAX, which is positive in this case, and the only other component is that's here in the x direction is F1x, which I just calculated to be 25 pounds. So because of that, I can rearrange FAX. If I cover that up, FAX minus 25 is equal to 0. So if I get FAX by itself, I add 25. That means that FAX is equal to 25 pounds. And that is acting up. We can confirm that that is true because we ended up with a positive answer. So let's box that answer. We'll add the direction since it is a vector. Okay? So now let's go. Sum of my forces in the y direction must be equal to 0 as well. Those are equal to, well, I have FAY plus FBY minus the y component of F1, which is going down because it was going down and to the left. So I'll say that's a negative 43.3. So minus 43.3 pounds minus, again, going down 50 pounds. And I can't do anything more with that because I have two unknowns and only one equation. So let's jump into our moments equation over here. So our three equations of equilibrium are our components in x, our components in y, and our moments. With moments, we get to choose which moments we want or where we want our moment to be calculated about, and I'm going to choose that always to be my pinned connection. So A and AX, AY are not part of the equation because they're at the point A. So because their distance is 0 away from A, they have nothing. Standard practice is that our counterclockwise moments are positive. Those are equal to 0. So what's causing a moment? Well, if I put my finger on the pin here and I point up, if I assume that that is pushing and this could freely spin, that would be causing a counterclockwise moment. So FBY would be a positive moment. And I don't know that value, so I'll write FBY. And remember, moments are force times distance, so I need to say FBY times 10 feet. And then my other two forces, since they are pushing down, they would be causing clockwise rotation. So both of these two y forces are going to be causing negative moments. F1x does not cause a moment because it is parallel to my moment arm. So I have minus 43.3 times 4 minus 50 times 10. I kind of run out of space there. Hopefully you can see. So 43.3 times 4 is 173.2. So I have FBY times 10 minus 173.2 minus 50 times 10 would be 500. Okay, and what I would do is I could combine these and add them to the other side. So plus 173.2 plus 500 plus, let's just combine those right now. That would be 673.2. So FBY is going to be equal to 673.2 divided by 10, which would be 67.3 pounds. And again, I could confirm that that is acting down. I want to draw my down arrow in there. So now I know that. I can plug that back in over here. Oh, excuse me. 67.3 pounds down. Plug that back in over here. So now I have FAY plus 67, sorry, it would be acting up. I apologize. Plus 67.3 pounds, confused myself there, minus 43.3, minus 50. So if I combine all of those together, I get, and I move all of that over, so all of this together would be equal to minus 26. 0 equals FAY minus 26. So if I add 26, FAY is equal to 26 pounds going up. There. So I have all three of my reaction forces calculated using my free body diagrams and using my rules of sine and cosine. Hopefully that helps. Go ahead and give this a practice. and we'll work from there.